So I'm a little early, but that's fine because I really just wanted to start off by asking how the quiz and the homework went. So how did they go?
Still need to work.
So okay. And it's not due until this Friday, right? So you all are not freaking out about it. The quiz is kind of hard. I'm not. I don't think you're too wrong about that. Did all the technical stuff work out? Were you able to like upload a PDF and everything?
But the technical needs to refuse to cooperate with me.
Oh yeah, calculators. I don't like them.
Just need to put it in. No, I was supposed to print out, but no, I was supposed to
I
print
recommend spreadsheets myself. It's a lot easier to tell. Well, you know, yeah, you just type in the numbers and make a little formula.
Somebody gets to that.
It's sometimes a lot easier because you can see like exactly what number you put in and fix it, which is what I like about it. Any other things that might have come up over the weekend? Everything good? Okay. Just so you know, I can't see anybody's noses, which is awesome, but please, you know, keep them up during class. And if you're online, please go ahead and mute out unless you actually want to say something, in which case, please do say something. Okay, given all of that, I think where I left off last week was we were kind of introducing electric fields. And we had talked about electric fields may be due to more than one charge. Okay, let's jump right in with that. Okay, and please forgive me if I repeat one or two pieces of information, which I might do. Share the screen. We're out of my time now. Here. Okay, and that's over there. Okay, cool, perfect. Electric fields. Where, again, I apologize if this is repeats, but for example, if this was the force between a charge capital Q and a test charge Q naught, the electric field would just be whatever you have left over when you get rid of that Q naught. So like the electric, so this right here would be the electric field. Okay, where the electric field due to some point charge Q is KQ over R squared in the R hat direction. Now, we talked about vectors and units. I did want to draw a picture just so I'm sure we're all there. If that's Q, and this is some point P, R goes from Q to P. Okay, so there's my R. And so this would be like the electric field at point P. Let me ask you, is there anything actually at point P in this picture? so if I have some charge, capital Q, and I say, okay, well, I want to know the electric field due to that charge at this point in space. And so R goes from the charge to that point in space. Is there actually anything at that point in space? Excellent. No. I see. Good. I'm glad you said that though, because that's the natural thing. Because we start off talking about a force between two charges. You want to say, well, there's like something there, right? But the whole point of the electric field is we just want to think about what this one charge is doing. We don't want to have to think about an interaction. I just want to think about what electrical properties is this one charge putting out. And so that's the big difference between a force and a field, or a force is going to be an interaction between two or more things, and a field is a product of just one thing by itself. Excellent. Okay, good start. Then we are going to say, well, clearly we could have two charges, because why not? And so we could have like Q1 and Q2 with whatever charge they have. And I could say, well, now I want to know the electric field at this point out in space. And so now the electric field at point P, so now that's going to be R1, that's going to be R2, that's an R, by the way. The total electric field will be the electric field of 1 plus the electric field of 2. And so we're going to have KQ1 over R1 squared in the R1 hat direction, plus KQ2 R2 squared, R2 hat direction. And there's a certain amount of combining that we will do, but there's a few things that I would like you guys to note here. One, this still isn't an interaction between two charges. This is the properties of the one charge plus the properties of the second charge added together at point P. Next, the R is not between Q1 and Q2. It's from each charge to this empty point out in space. And it kind of an addendum to that, the R1 hat and the R2 hat, they're not the same directions. There, you see the way R1 is pointed and you see the way R2 is pointed. Those are the directions for R1 and R2. It's, yeah.
So with the R hat, we're not actually like multiplying by anything with that. That's just for direct.
Yes, I'm so glad you asked, because a lot of times it doesn't get gone over in Physics 220. Anytime you have a letter with a hat on top, what that is a unit vector. And so it's got a magnitude of 1. So like when we have the R hat here, we're just multiplying these things by 1. Is that going to affect the overall quantity? No, right? So that's why it's called a unit vector, because you can multiply it into anything and it's not going to affect the magnitude. But all it means is in the R direction. So yeah, you're not multiplying by a variable R. You're just using a shorthand to say in the R direction, or like in the negative R direction. Negative R direction. Does that make sense?
Yeah.
Okay, just making sure, because we're going to keep using it a lot. Same thing with X hat and Y hat and Z hat as we go through. Okay, so that's good so far. Okay, so and we can kind of wrap this all up. Well, okay, let me say 1 or 2 more words, and we can do a problem on this. I have a problem pulled up on this one. Don't forget that when you're adding vectors, you have to add them as vectors, which means split them into X and Y components, add the X's and add the Y's separately. And then if you want to have like a polar form, put it back into a magnitude interaction. Vaguely familiar from physics one? Okay, yeah, I just did that lecture in physics one today, so it's like, yes, I can talk about this a lot. Okay, so yeah, so if I wanted to shorthand this into a nicer formula, what I would write is I would say, well, no matter how many electric fields I have, they're all gonna have that K in them. So I can pull that out. And then everything else is gonna have a QI over R sub I squared in the R sub I hat direction. And I am summing over I. And that would be the total electric field, no matter how many charges I have. I can just plug it into that. Okay, should we go ahead and do a problem? Okay, good. Sounds awesome. And a good problem to do is this number 21 in the homework. Okay. So for number 21 in the homework, we have an equilateral triangle, which is nice of this problem, that has three charges, A, B, and C. And so we have these sides. And I'm gonna say this distance D, they give me a number for it. And of course, since this is equilateral, it's the same distance between each one of them. Okay. And they also give me the charge of each one of these point charges. I have an NC here. What's the N stand for? Nano, perfect. So these are all, this is like 1.1 times 10 to the negative 9th coulombs. Okay. What we want to do is we want to find the electric field at the center of this equilateral triangle. It's kind of a long problem, so buckle in. Okay, so the center of this equilateral triangle, this point P. Again, is there anything at that point P? No, yeah, just an empty spot in space where we want to figure out the total electric field due to A, B, and C. And so I might not make it to the end, but let's just like go through and show how this is going to look like. I want to start with QC because that's actually the easiest. Well, I don't know if it's easiest. It's pretty easy. QC. Okay, QC is negative 5.1 nanocoulombs. So do we expect the electric field from C, I'm going to color it blue, to go towards the charge or away from the charge? And did I mess up which one was negative? Thank you so much. Okay, QC is positive, clearly, right? Okay, so if QC is positive, should the electric field go towards or away from it? Away. Okay, so QC will have some electric field in that direction. With a magnitude of K QC over R squared. Now, first question, this is an equilateral triangle. Point P is in the center of this equilateral triangle. So when we say the electric field is pointing away, we mean the electric field points along that direction, which kind of bisects that angle. What direction is the electric field in? And give me an angle. Very close. 660 is where you should start. 30 degrees? Yeah. So yeah, this whole thing is 60. You're at the right starting point. And yeah, since we're kind of bisecting that angle because we're going towards the center, this right here is going to be 30. So this is at 30 degrees. So far, so we're not choosing at random. We're okay. No. I'm glad you caught that. Yeah, equilateral triangle. So we know all the angles in the triangle are 60, and so half of that angle will be 30. Okay, this looks really good. The next bit of geometry we're going to do is we're going to figure out R. And I'm gonna go back to this page. I have an equilateral triangle. I know each side is some distance d. I need to know that distance r. What are your thoughts?
Break it down into it's up down part, and then it's you can break it up into like a triangle. So like you find
okay, you could break it out. Triangle is that?
Yeah, when you like a right triangle.
Oh, nice.
Right there.
Like that? Is that?
I was talking just keep that.
Oh, keep going. Oh, that's a good one. I hadn't thought of that. That's a better idea than mine. Okay, so so this whole thing is 2r then, right?
Yeah.
That side right there. That's 90 degrees.
Yeah, would that be too long?
Well, so r goes from the edge to the center. Would that be 2r? It wouldn't be 2r. It wouldn't be. You're right.
We would have half d on like the sandy side.
Yeah.
D on like the bottom.
Yeah. So I'm not sure I do like your idea better than mine now. Yeah. Okay. No. I thought that was almost brilliant.
So is this
Close.
a good idea or a bad idea?
Yeah.
Because
Okay.
more geometry, it's a bad idea.
Let's go with this one then, because I know this one will get us there. Because so now we have this triangle like this, where that's d by 2. That's the thing we want. That's 30. And so this is a 30, 60, 90 triangle. Let me draw it a little bigger so we can all be happy about 30, 60, 90 triangles. Does anybody know the ratio of sides for a 30, 60, 90 triangle? It's 1, 2, and the square root of 3, right? Okay. So 1, 2, and the square root of 3. So the square root of 3 over 2 is the same as d over 2 over r. So r equals square root of 3 over 2. Nope, not like that. Sorry. 2 over the square root of 3 d over 2. D over root 3. So I said I have a ratio of sides. So I have root 3 over 2 should be the same as d over 2 over r. Believable? Not believable? Okay. And once you have that ratio, because similar triangles means I can't just say like r is 2. I have to make that ratio where they're the same. Now I can just take this and I solve for r. And so I multiply both sides by r, divide both sides by root 3 over 2, and I end up with d over root 3. Okay. If I got it wrong, please let me know. It happens. And so what's going to be really nice now is I can write that down up here, because it's going to be true for all 3 of these things, right? So that'll be the magnitude of the distance between any of the points and the center. Okay. However, this doesn't fix what I really need fixed, which is I need this electric field in X and Y coordinates, right? So let's do that. So for the X component, about to try to make this a little bit prettier. So there's my electric field. There's EX. There's EY. Can you guys kind of all did. That angle is 30 degrees. How would I find the X component? With a sine or a cosine? Cosine, right? So I take the hypotenuse of the triangle, KQC, and I'll make the substitution now. D by root 3 squared times the cosine of 30. Okay. And Y would be the same thing, but with the sine, right? D by root 3 sine 30. Reasonable, everyone kind of happy? Okay, let me put this on its own thing. So the electric field due to C is K QC and since we're squaring that, I'm just going to say D squared over 3 to not have to pay attention too much to that root anymore. Cosine of 30 in the X hat direction plus the same thing but with the sine and with the Y hat. Okay. Okay. That was just one of these 3 charges. However, there are some tricks we can play, right? Like this should be very similar for all of these. So if we looked at B over here, you know, its R would look like that. Its electric field would point in that direction. The angles would be the same, but just in the opposite direction. So we could write down something really similar. So like for the electric field here, if this were B, I'd still have my K. This would be QB. The R would be the same. I could still say I have a cosine of 30 here, BX. But what would definitely need to be different? And that's what's is it pointed in the same direction? No, is it pointed maybe in the opposite direction? And we could denote that by a minus sign, right? Okay, so over here, EB, we'd have something super similar, cosine of 30, but I just put a minus sign right there. And this is, yeah, that's B. Okay, I remember that. What about the Y direction? Is the Y direction going to be positive or negative? So for this arrow right here, it's in the negative X direction, but is it in the negative Y direction? I like the no. Okay, so that one's just going to be the same. KQB, B squared by 3, sine 30, Y hats. Okay, last one. QA. So it's at the top here. I need to circle back. Oh, no, I don't. No, I don't. I'll be fine. QA. Which way is its electric field going to point? Down? Okay. So if I ask you for the X component of A's electric field, what would you tell me? What do you think? The X component of an electric field that points straight down. 0. I like zeros. Okay, so we can say 0 in the X direction. And then the whole thing would just be in the Y direction, right? K, QA, D squared over 3. I don't need to put like a Y, I'm sorry, a sign of anything. I do need to put a minus sign out front because it's pointed down and not up. Okay, I think I'm about to call. Yeah, I'm pretty close to calling this because I don't want to do the next treacherous bit of math. But I do want to note a few things before I start on that. One is I didn't really touch on the fact that QB is negative because that'll flip all our directions though. Does that make sense? Because if it's positive, it'll go out. If it's negative, it'll come in. So, but I did that because I'm going to assume that when you plug that number in there, you're gonna keep the minus sign. And so when you plug in a minus sign here, instead of being in the negative x hat direction, it'll be in the positive x hat direction. And here, instead of being in the positive y direction, it'll be in the negative y direction. Is that okay with everyone? I hope so. Okay. And let me ask you one more question. So after you do the nasty work of adding all these things together, I believe in you. You'll end up with like the total electric field equals some amount of electric field in the x direction and some amount of electric field in the y direction, right? How would you find the magnitude of the total electric field? What do you think? You find the hypotenuse. And so anytime someone asks you for a magnitude, what you're really doing is a Pythagorean theorem, right? And that's if you're in 1 dimension, 2 dimensions, 3 dimensions, however many dimensions you want. Square each component, add it up, take the square roots. And like I say, it'll work in 1 dimension, it'll work in 2, it'll work in 3, whatever you want to throw at it. It's a pretty good equation. Okay, so the magnitude of the electric field. You can just do this. How about the direction? How would you find the direction of the electric field? And let me tell you, so it looks like so just looking at this picture, it looks like this is probably going to have some EX like that, and our EY is probably going to be negative. So you just told me how to find the magnitude. I'm asking for direction, I'm asking for that angle right there. How would you find that angle? A tangent. A tangent would be great, right? Yeah, choose your favorite trig. You can always say that whatever angle will be the inverse tangent of the y component over the x component. And that'll give you the angle from the horizontal, which is the angle you should be giving me anyway. Vaguely familiar from last semester? Okay, okay. You guys do not look happy about that. You want to talk about it? Or should we do some more intense math? All right, let's do some more math. Because the next thing is actually pretty cool. So we just did a triangle. Clearly, I could just keep throwing charges on this board and we just have to add up each and every one. However, at some point, when you start throwing more and more charges on a board, at some point, they start looking continuous. And instead of having just a bunch of different discrete point charges, you have some sort of surface that is charged. And now, instead of using a sum, k q sub I over r sub I squared, you of course would want to integrate each little chunk. K dq over r squared r hat over q. Okay, that looks pretty good. Looks great, in fact. And okay, let's point out a few points here. One, what are we integrating with respect to in this integral? Q. It says dq, right? So we have to be integrating with respect to q here. And this thing right here, so that's our limit of integration. And that says just keep adding up dq's until you've reached the total charge q. Okay. Now, if I'm going to keep drawing this picture here, let's say I have my point P. So I have my weird charged surface. I have some point P out here. I can split my charged surface into a bunch of little dq's. So that's the first dq. There's a second dq. You know, I could chunk up my little surface into all little bits of dq. Is R going to be the same for each of those dq's, or is it going to be different? Different. Different is the right answer. Because for each little dq, it's in a slightly different spot, right? So each of those r's is going to be slightly different. So the real difficult part about this integral is the fact that r generally depends on which q you're choosing. And so you have to find a way to relate r to dq, some function that relates those two, which we will do. You also probably noticed I drew this somewhat irregular shape, and it's not a very nice shape, and you're probably wondering, how would you ever figure that out? The answer is you would probably never do this for this shape. This would be a bad, if you look at this shape and you said, I need to find an electric field, don't try to do it using this equation. Okay. Another thing I'd like to point out is you might say, what sort of weird surface is going to, no, you're not. No, you're not. I'll talk about that some other time. Sorry, not the right time and place for that. But the right time and place right now is let's go ahead and do a problem that we can actually do with this equation. Yeah.
Is it going to be more like a straight line?
Yes, like number 20 in your homework, which I'm not going to do exactly number 20, but I'll do the one I have written down. The electric field of a charged rod, length L, should I do that one first? There's a, yeah, I should. I'll do that one too. But yeah, I should. Okay, electric field of a charged rod. Okay, so I have a uniformly charged rod, and there's a few key words here we're going to talk about. So this is uniformly charged. And that means the charge doesn't collect on one end or another, it's just spread out evenly. Total charge Q. Charge Q. Length L. And I want to know the electric field, some distance A, that's an A, from the end of the rod. Sound okay? So I want to know the electric field right there. So, for the purposes of this problem, we're going to consider this to be a really thin rod. So we're not going to consider it to like have a lot of Y and Z. We're just going to say, hey, it just exists on the x-axis. Let me throw an x-axis through here. X, like that. Is that all I need for the moment? Yeah, okay. Okay, let's do this. This is a positive Q. Let me ask you if this, so like there's positive charges, you know, kind of all up and down here. Do we expect the electric field at point P to be in the positive x direction or the negative x direction? Positive. Good. Okay, so we expect something in the positive x direction. Okay. There's a few more things that we can kind of give ourselves some space on, like some limits to think about. One is, I know that the electric field here should be less than K Q over A squared, because that would be the electric field if all of the charge were right there on one end. And since I know the charge is spread out, some of the charge needs to be further away from that. So I know I need to be less than that. Okay. Let me do the other side. The electric field should be more. So what should the electric field, what would the distance be? What should I put in instead of that A if all the charge was right there? So if I had one big charge, total charge Q right there, what would you put in for the distance between point P and the end of that rod? L plus A. L plus A, because that's starting here and then the entire length of the rod too. Does that make sense? Okay, so that's just kind of like the starting point where we might want to think about what kind of answer we expect to get and how it should look like. So I know it should be in the positive x direction. I know it needs to be less than KQ over A squared. I know it needs to be more than KQ over L plus A squared. And so now let's start doing this. And if at the end of this, we're going to go back and we're going to like say, clearly we were right, or wow, we dropped a minus sign somewhere. That's a little lengthy. I don't need that much. There we go. That's what I need. Okay. This is length L, total charge Q, point P, that is A. Okay, so we approach this equation, R squared in the R hat direction, with the idea that we're adding up DQs. So it's a good idea to first draw a few DQs on here and kind of get an idea of what we're actually adding up. So let's draw our DQ. So like that would be a DQ right there. You know, that would be another DQ. And so I would add them up all up and down this rod. Okay. For each DQ, I have an R that looks like that. That goes from the DQ out to the points. Okay, so far so good. Let's so okay, sorry. As I choose different DQs, is my R going to stay the same or is it going to change? It's going to change. Okay, so we need to find a way to relate R to DQ. Fine, sure. Let us first write down some things where I'm going to draw, put a 0 here. And let me just make sure where I want to put my 0. I think I want to put my 0. I think I want to put my 0 right here. X equals 0. Okay, there's my X equals 0. So that means this is X equals L. That means this is X equals L plus A. All right. For the green line that I drew for R, could you express this as some combination of X, L, and A? What are your thoughts? A plus L. Okay, yes, you got it. Okay, so let's go through what you just said. So I'm finding the length of that line, right? Okay. Well, it starts at X. So X, of course, starts from 0 and goes out to wherever you're going to. So it starts at X. Then it goes whatever the length of this bar it has left. And so that distance would be L minus X. Does that make sense? So I have L minus X. And then we just have A to get through. So plus A. And so as like you said it, A plus L minus X, that's a good way to write that down. This equation that we wrote down, would it work for any points along that bar? Yeah. Yeah. So yeah, any like DQ chunk I took out of here and we drew the R for, we'd end up with that equation. Okay, that's good to have. And that's good to have because now when we're relating our DQ, we really just need to relate it to X instead of R. And that'll be a little easier. And so, does anybody remember doing center of mass integrals in your intro physics class? Nope. All right. Well, if you had remembered it, you would remember your professor saying a lot of things about uniform density and saying, wow, you can relate this length to your mass because you can say, well, something with uniform density will have the same amount of mass in each little chunk of length. And that's what we're going to do here. Well, this was uniformly charged, remember? So no matter which little chunk I take, the amount of charge per length will stay the same. So I can say dq over dx, where dx is the length of one of these little chunks, is the same as the total charge over the total length. And this, you will see this written down as like a linear charge density. I think the book uses lambda for linear charge density. But you can have like area charge density, you can have volume charge density. It's just total charge over total length, area, or volume. Okay, now I can solve this. Let me do the algebra here. So dq equals q over L dx. The capital Q and the L, are those things we know or are those things we don't know? We do, right? Those were given in the problem. In the beginning, we said, hey, this has a total charge Q. That's how we know it. We were said, hey, that's what we know. This has a length L, so that's what we know. We also know A there, kind of beside the point right now, but that's one of our knowns. And so now what we have is something that we didn't want there. We don't want that dq. Something we do want, we did want it in terms of x. And the other two things are just kind of knowns, they're constants even that we can carry around pretty easily. So what we're going to do is we're going to substitute this into our dq in our integral. So looking at this integral right here, we're going to say k, and it's instead of dq, we're going to write q over L dx. Q over L dx. We'll still have this craziness at the bottom. And we'll still have something in the x hat direction. So far, so good. I'm going to talk about the limits in a second. But let's do some integration and solve this thing. Okay, so capital Q and L, are those constants or variables? Constants, perfect. So we can just take them outside of our integral. So I have K, I've got Q, I've got L. What do I have left? I have dx over this thing, which is kind of ugly, and we will deal with it as we do. I'm going to carry that x hat around. It's really not going to do anything. It's just a constant, says in the x direction. I could drop it now and bring it back at the end, but it's nothing. It's not going to do anything. Okay. Now looking at this, I have a plus L minus x. The little a that and that L, are those constants or variables? Constants. So I can't take them outside because they're squared and they're kind of messed up in that. But I could do a U substitution kind of easily. And that might make this look a lot prettier. So I could say, well, U will be a plus L minus x. So du, I don't need to worry about the a or the L. That'll just be minus dx. Sound okay? Okay. So let's make some substitutions. So du equals negative dx, or dx equals negative du. U equals a plus L minus x, so this is u squared. I've got an x hat. I'll take that minus sign outside so we don't have to look at it for another 2 steps. What is the integral of du over u squared? That would be 1 over u. We're not that far yet. Let me write it in a slightly different way, and you guys might be happier. U to the -2. Can you do it in your head now? That's okay. We are going to remember that when we integrate, we add 1, and then we divide by whatever we have. So we just do the opposite of the power rule. And I shouldn't, I've diverged from my notes, and it's going to bite me in just a second. But if we add 1, we have u to the -1. So we're dividing by u to the -1, and then we just have like that. And if you ever need to check it, you just take the derivative of that, bring the -1 down, and you have a -2. Okay, it works. Okay, now a few things. One, which I'm really pleased with, what's happening to my minus signs in this equation? They're canceling because I got 2 of them, which is really nice because I needed this to be in the positive x direction. Second, I said that we would talk about limits, and now we need to, because our original set of limits was just q, right? Add up all the charges until you hit q. But then we switched to dx. And so now we need to switch our limits to be in terms of dx. So now instead of adding up dq's, I'm adding up dx's. And so where should I start adding dx's, and where should I end adding dx's? So where's a good place to start adding the dx's? 0, good. So I'll start adding dx's right there. Where should I end adding dx's? L is a solid choice. I'll stop adding once I hit the end of the bar. 0 to L. Okay. Excellent. I'm also going to cheat a little bit by substituting in for my u. So I have that. And let's plug in stuff and see what happens. So I have kq over L out there. Then I have 1 over a plus L minus L minus 1 over a plus L minus 0, all in the x hat direction. Okie dokie. This is interesting. So I have a plus L minus L. What is that really? A plus L minus L. A. Okay, so this is really 1 over A. Okay, and then I have a plus L minus 0. Okay, well that's really just a plus L. Okay, that's a start. It's not the worst start. That's not even a bad answer. Let me rewrite it so we can kind of start to get our heads around it. Q over L, 1 over A minus 1 over A plus L. Okay, x hat. Okay. It's not even a bad answer. Let's go back and compare it to what we're looking for, and then talk about whether we want to simplify this or not. Okay, so we started with this set of ideas. Okay, did we get the first? Yeah, we did. It's in the positive x direction. That's pretty solid. Okay, now let's look at these second two. It should be smaller than kq over a squared and larger than kq over L plus a squared. Well, KQ over LA minus KQ over LA plus L. Well, first off, do we have the right set of units on this? Are my dimensions right? I need a K times a charge divided by a length squared. Okay, so I'm pretty good there. Is this smaller than KQ over A squared? Well, I would say definitely yes, because we start off with KQ over L times A. That in itself is less than KQ over A squared, because L is bigger than A. So that's smaller. And then we're subtracting something else off. So that's pretty solid. And it should be bigger than KQ over L plus A squared. And I think it is. Because I think it is. I don't know if I have a good way of expressing why I think that is. Do you guys have a good way of saying why this should be bigger than KQ over L plus A squared? Maybe. And this is where you would do your math, just so you know. You'd say, well, this is L plus A minus A over L plus A. Your A's would cancel. KQL over L, A plus L. And at this point, you'll tell me I've done something wrong, right? Yes, I have. There we go. Okay. I should have done that. That wasn't too hard. You can find a common denominator inside your parentheses, right? So you have A plus L minus A on the other side. On the bottom, you have A times A plus L. Your A's cancel, and then your L's cancel. And you end up with maybe a much more easy to see thing. KQ A times A plus L. And now this might be a lot easier to compare to these two things. I probably should have started there. Yeah. Where A plus L is more than A. Okay, so it's definitely less than KQ over A squared. And A is less than L plus A. So it's definitely more than KQ over L plus A squared. Yeah, that was much better. I should have gotten ahead and done the extra step. I was being lazy. Okay, but I do want to talk about this a little bit, because what you kind of see here is the equation we ended up with is midway. I don't want to say it's midway between the 2 points because we have squares, but it combines the two. Instead of KQ over A squared or KQ over L plus A squared, it's KQ over A times L plus A. So that's, you can kind of see it's taken into account the endpoints and the fact that it's somewhat of a combination of if the charge is on one side or the other. Sound okay? Bit much, but did we make it to the end okay? Or okay, so we have another if you want. We have another we can definitely do. There's another one from the homework that we can kind of look at. But just to kind of go through the steps here, write down your general equation there. Draw out what you're integrating with respect to. So like draw chunks of DQ. Then try to relate your R to your DQ. You'll generally do this through some density thing. Make sure you're writing everything down in terms of your coordinate system. So here my coordinate system was X. You might find your coordinate system turns into like an X and a Y, depending on the shape you're dealing with. Then once you have everything written down in terms of the same variable, that's when you're integrating. And that's really the hard part is trying to make sure everything's written down in terms of the same variable. Okay, big chunk of math. Should we do the charged ring? The answer is yes. Yeah, we're told. Yeah, we're totally doing the charged ring. This one goes a little bit smoother. There's a weird integral, but this one goes a little bit smoother. I'm gonna start this. Hopefully, I'm gonna finish it. I also, when you go home today, I want you guys to look at number 13 in the homework, which is about forces instead of fields, but it has the same thing where you have to chunk something into do an integral and chunk it into chunks. I want you to give it a shot. And that's definitely one we'll do in class on Thursday if you can't do it solo. But I want you guys to kind of give it a shot based on what we've been doing today. Okay. So, but I do want to do this ring because we're going to come back to a charged ring as we go through electric potential in a week or two. So I want you to see it in a couple different ways. Okay, so we have a ring. Total charge Q, uniformly distributed. Radius A. And what we're going to be looking at is a point P out here, which is a distance. Are we going to give it a distance? The distance X from the center of the ring. So we're looking along like the center of the ring. So we're going to say things about symmetry. And so we want to figure out the electric field just at that point. Okay, first off, does this make sense? Can you picture that in your head? Okay. Next, let's talk about what we expect to see. Do we expect to see, let me give you a coordinate system. I haven't given you a coordinate system yet. So that'll be the X direction, that'll be the Y direction, Z direction is coming out of the screen towards you. Do we expect to see an electric field in the Y direction? No. And why not? Okay. So yeah, the electric field from the top of the ring will come down, the electric field from the bottom will go up. And so we expect to see the ups and downs cancel out. What about the Z direction, coming out of the board towards you or going into the board? Do we expect to see an electric field in that direction? They absolutely do cancel out too. Okay, so that means the only thing we expect to see is an electric field in the X direction. So all our Y and Z components we expect to cancel out and then just have an X component left over. Okay, does that mean that we can just say, well, the electric field is clearly just KQ over X squared? Is that a good answer? Where X is that distance right there.
Yes, but I feel like I'm wrong.
Yeah, no, I made this mistake when I was a freshman, where all your X's and Y, all your Y's and Z's cancel out. So surely you can just use the distance in the X direction. But I want you to think really hard about what that R is going to be. Where when we start chunking this up, like that'll be a DQ, right? And that's going to be R right there. So will I have, is DQ closer to that point, or is it further away than if I had all my charge in the center there? Yeah, so if I had all my charge in the center right there, it would be closer to that point P, and therefore the electric field would be stronger. If I put it in a ring, I've moved the charge further away. And so this equation won't work because that'll be too big. Okay. Okay. So let's since we can't take the easy route out, which you should always try for the easy route first. Let us start doing the more difficult things. Now the first thing I want to do is I want to, since we all just, yeah.
Sorry, would that equation work instead of using x squared? Would you use the magnitude of r?
That's a good question. If you did that and you just said, well, let me say, if you just said KQ over R squared, what that would mean is that you had all the charge right there. What that wouldn't do is account for the canceling out of the Y and the Z directions.
But we already know the y and the z is going to
Let's go one or two steps, and I think you will see kind of exactly where that's not a terrible way to look at it, but you need to account for one or two more things. Okay, so we know EY and EZ are 0, so we're just looking for EX. And so if I have a total field, let's just do it for this little DQ. So the electric field of that little DQ, I'll call it DE, is KDQ DQ over R squared in the R hat direction. My D got away from me. There's my R. The electric field due to that guy would be like that, DE. And I could, and I'll just do like the electric field in the X direction and the electric field in the Y direction. There could be a Z direction too, but we'll say by symmetry at the end of this and not worry about it too much. Okay. I know my DEYs are canceling out. Okay, so that means I really just want my DEX. Okay, is there a way to get just the X components of that DE? And if I asked you to pull off an X component of anything, what would your first try be? If I say you needed to split this into X and Y components, what would you go to? Yeah, you go to your trick, right? You'd say, well, I'm probably going to use sine and cosine. And you'd be right to say that. You'd say, well, we'll try to figure out that theta in a second, but clearly DEX is going to be DE times the cosine of theta. Okay, and so I think this is going to answer your question, by the way. It's not that you want KQ over R squared, it's that you want KQ over R squared times the cosine of theta. Okay, getting really close. That was kind of the conceptually difficult part. Let's figure this out. So DEX equals DE cosine of theta. We need not just one little component, we need the whole component. So we're going to integrate all of that. So that'll be the electric field in the X direction equals the integral of this whole thing. Let me go back a page. K dq over R squared. K dq over r squared. I shouldn't have integrated that. That was bad. In the times cosine of theta. Okay, and since we pulled off the x component, this has to be in the x direction. Okay. Okay, so far so good. Did everyone kind of get that DEX versus DE thing? Would anybody like to ask like 20 questions about that? Okay, I'll wait for your questions on Thursday. I'm sure they're coming. But that was, in fact, the hard part, because let me ask you, as I go around this circle and I pick out different chunks of DQ, and I try to relate that to my R right there, is my R going to change its length, or is it going to stay the same? It's going to stay the same. Going to change direction, but I already dealt with direction. So I can, it's just a constant. So I can just take it outside of my integral and not think of it for a few more steps. So K over R squared. How about this angle? Theta. So that angle right there. Like certainly we're going to rotate around, but will that angle stay the same, or will it be different? I'll say the same. Excellent, excellent. Way to rotate that in your head. And so then we're just integrating dq, and my limits are the same as the limits I started with way back when, and even x hat on the end of that. I'm just adding up all the dq's. And so what is the integral of dq with respect to q? What are we gonna get? I like 1, but because you normalized it, which is excellent. You mean capital Q though in this case? Yeah. No, actually I like 1 better, but okay, we have kq over r squared times the cosine of theta. Okay, this is all really good. And all we have to do now is we have to go back to the beginning and we have to say, okay, can we express this in terms of our knowns? Because theta actually wasn't one of our knowns, right? What our knowns was x and a. Okay, so first off, r. Can we express r in terms of x and a? Maybe through a Pythagorean theorem, where that side is a and that side is x. Okay, so that means that r squared will be a squared plus x squared. Okay, so that's kq. And that shouldn't be squared. I got a little excited with my squareds. A squared plus x squared. And I don't need to like square root it or anything because my r is squared already. Okay. Then this cosine of theta. This one's a little bit trickier. Let me erase some stuff. Okay, that's a, that's x. But let's start by asking, is that theta the same as this theta? All right, little opposite interior angles there. And so if you had a cosine of theta for my big red triangle, what would you tell me the opposite and the hypotenuse were? Not the opposite, the adjacent and the hypotenuse. So cosine of theta is adjacent over hypotenuse, right? X over r, I heard it out there. Excellent, okay. X over r, where r is a squared plus x squared, right? So x over a squared plus x squared. And that is square rooted because that's not squared already. So far, so good. Okay, and we're pretty much the end here. Let me which is good because I'm out of time. Let me simplify this down a little bit. So we'll have kq times x, and then on the bottom we have a squared plus x squared to the 3/2, because we have 1.5 a squareds plus x squareds, and that's in the x hat direction. I want on Thursday to start off here and double check against some of the limits that we talked about, you know, like whether it should be bigger and smaller than. And then if you guys want to do that force problem in the homework, I'm happy to go over that. It's like the force between a point and a rod or something. And if there's any other homework problems, let me know, because I need to do a little bit about electric field drawings, but we are close to the end of chapter 5. Yes.
For some reason, I don't know how I'm gonna approach the first one.
Oh, okay, yeah. It's given a charge. How many electrons were okay, so here's
All right, I was supposed to warn you about that.
so
I forgot to mention about that, but apparently.
made up of like protons
Yes,
and a bunch of
if you're a
electrons.
chemical programmer, just use Windows.
That is crazy.
Yeah, but if you're a
So your
serious
net
programmer,
charge,
use
that's
MacBook,
what
but
they
now
do.
MacBooks slowly.
Right. Yeah, and so that happens because
Well,
you have
actually, no, the
some number
design
of electrons
hardware not so
more
much.
than. So what it wants you to do, charge on an electron is 1.6. So that we want you to take this net charge
Did everyone leave the Zoom call or no?
by the charge of an electron, and that'll give you the number of electrons.
Yeah, I didn't think that I could just use that. So there was like a lot more to a copper penny than just.
This is such a cool thing. We have never split the electron up. So that's like a quantized amount. You can't have half of that. You have to have this.
Oh, so it's just always no matter like the size of that.
Yeah, you have 0, this, twice that, 3 times that, but not half of that.
I got you.
It's
That
very
makes
fundamental right there. Hi.
For the lab LBC, you said I can enter any lab for either Wednesday or Thursday.
Yeah, just go to a different lab section.
All right.
You can. I'll let the lab instructor know like who you are, and where you're from.
Is it the same lab instructor? Or
It will be a different lab instructor every
Okay.
time.
I'm not sure if it's the same one I had for Friday or it's a different.
I do not have them memorized,
Okay.
but you just let the lab instructor know what section you're from and who
Alright.
your usual
Okay.
instructor is, and that's all you need to
Okay.
do.
All right. Thank you.
Hi.
I have a question. If you had any more space in your lab section, the L9 and 232 on that.
Give a sec. Let me look at that.
Send you an email. Though.
I'm really sorry. I might have missed your email.